Welcome back. We spent a lot of time looking at how to resolve forces, looking at 3D objects, finding centroids, and looking at fairly simple setups in order to be able to identify what's happening with those forces. You can imagine we started off with a barge being towed by two ropes, and we've kind of extended the complexity a little bit since then. Today, we're going to take a major step forward, and we're going to start looking at more complex structures. Fortunately, the same tools we've used previously can be used in this one. Now first, I'd like to show you what I mean by that, by complex structures. Let's take a look at a simple bridge here. It's made by connecting these members, these metal members, connecting them together at the end points, and generally forming triangles. This is what we call a truss, where we take a bunch of these members, we join them together. And you can imagine that if you have a truck force there, or a truck parked there, you're going to have some force on this side and some force on this side. And the real question is, well, how thick do these members have to be? There's a good question. We're going to get into that. Those trusses follow everything from something very simple like this to maybe getting a little bit more complicated here. Once again, you can see the triangles, and you'll see that in almost all trusses. Here's another truss going across the top of the bridge. Finally, we can take a look at a little bit more modern truss right here. This is called a K-truss. There's tons of different types of trusses. We're not going to cover too many of them in these modules, but it's good to know that there's some basic templates that they follow. Now, the next thing, the good news is, as you look at those trusses, they look way too complicated to figure out what's happening. However, the good news is we've already somewhat learned what's happening. We just haven't seen it from that perspective. What we're going to do is see how powerful some of the tools we have already are. So when I come home, if I'm walking, a lot of times what I'll see is I'll walk along, and here's a telephone pole. And we'll put the sidewalk here for reference. And we'll give me a little stick figure. I'm walking along the sidewalk, I'm walking away from me or something like that. And there's this telephone pole. There's a wire going across the street. And then I notice there are these supports. These supports sometimes look like this. Now, of course, this isn't quite to scale, right? I'm not going to have that support right over my head, but you can imagine this right here is a cable, and we'll color the telephone pole so it looks a little right here. There's our telephone pole. And I might ask you a question. I might say, what's happening if the tension in that electrical line, or we're sticking with telephone pole, so the telephone pole is 400 newtons. All right, well, what's happening? Mainly, maybe I'd ask a better question. I would say, if the force of this tension is 400 newtons, what is the tension in this cable right here? What is the tension in this cable? That's actually, a fair question to ask. Now, fortunately, you already have the tools, your toolbox, to be able to solve this, provided let's say say that's a 45-degree angle, okay? Now I ask the question, what is the tension in the cable? We'll call that force C. Your first action is your free body diagram. We're going to have over here, we'll put the force, the tension right here, and we're going to build that free body diagram around this point. We had the force tension here, the force of the cable here, and then finally we'll have the force of the pole. We'll just say that it's going down. We don't know which direction it is. The force of the pole right there. Let's build that to scale because that'll matter. There we go. The force of the pole right there. Now to solve this, you already know what to do. We'll go through this pretty quickly. You can either resolve this in the x direction, in which case we know that the force, the tension in the x direction is 400 newtons. So we say the sum of the forces in the x directions is 0, and that is negative force T minus sine 45 times force of C. And we can solve that, and we'll see that. If we do that, force C equals about 565 newtons. Another way that we could have done this is we know that the horizontal tension force of T is equal to the horizontal in the force of C, the yellow. Well, it's a 45-degree angle. So that means that it's 400 newtons horizontally for force of C, 400 newtons vertically, and we're looking for the total force. Now you're going to take, you should know this by now, that's going to be the square root of 2, 1.414. In other words, force of C looks like this. 400 horizontally, 400 vertically. That means we're at about 565 diagonally. Any of these will work. But what I want you to notice is that we took a look at this one point. Around that point, we know the forces are all going to sum to 0. As a matter of fact, if you're kind of savvy, you might have even remembered your force triangle and done force of T this way. There's all sorts of options that we have, lots of tools in our toolbox. But what's important to know is we figured this out around a point. We call this technique the method of joints, because what we're doing is we're looking at each joint, summing the force around that joint to 0, and then using our knowns to figure out our unknowns. The method of joints takes a look at pivot points, joints where members come together. We take a look at, and generally you look at the area where you already have a known, and then you use it to find an unknown. By using this, we can start in one area of a truss and slowly build up to be able to solve all the components of the truss. Now you know enough now that if we wanted to, something else we could do is we could use the method of joints to solve for what's happening at this point right here. Now we know that the force of the cable goes that way, and we'll call it the force of the support. We know it's going to be pushing in there, right? The force of the support, and then we'll have something below this force right here. We'll call it force lower. Now, you already know how to do all this stuff, but I want you to see that this is simply by looking at one joint and identifying all the forces, or summing all the forces around that joint to 0. We can use the same in trusses. Thank you very much, and on our next module, we're going to cover a different way to identify forces through